We're going on to work on a review of a Chapter 7 test. These are generated by the textbook authors, and we're dealing with radical numbers. So our instructions assume that variables can represent any real number, and we are asked to simplify that. Okay, so let's get started. Now, we're using techniques that we had in class, and basically, when we go to simplify, we're trying to think of factors of 63. Are there any perfect square factors? And the answer is yes. It would be 9 times 7. So using this technique of breaking the radicand into two factors, one being the largest perfect square. So this would become 3, the square root of 7. You have simplified that. Now as we go down to number 2, we see in the index number position there is a 3. And there's a negative sign under the radical. Well, as long as it's not even index number, a negative sign is okay, as long as it's odd. So this is going to be a negative, and then the cube root of 8 is 2, and the cube root of 9, x to the 9th power, we're just going to use that index number and divide it into 9, and we get x to the 3rd. All right, there's a perfect square already, so that's going to be a 10. And the square root of a squared, again, there's a 2 there that we're going to divide this by 2, so this just becomes a. Now, for number 4, you have to keep in mind that that happens to be a perfect square trinomial there as the radicand. So in a sense, this is x plus 4, the quantity squared. If we expand that, we get this. And there again, our index number is 2. So for number 4, this just becomes x plus 4. That is, we divide this 2 into this 2, and it just becomes a 1, and there it is. Now we're going in to see how fractional exponents relate to radicals. Well, we're going to make a radical sign. Now this exponent is 6/5. I don't like the way they write it like that, but this is good. Now what we do is, whatever the base is, that becomes our radicand. And we can put it in parentheses also. So 3a squared b. Now the fractional exponent, the denominator of that fractional exponent is actually our index number. And the numerator, that's the power to which it's raised. So that would be writing it using radical notation. This is a fractional exponent notation. So these two are equivalent. And here they want us to do just the opposite. So it's going to be 13xy. And you could put that in parentheses because that is your radicand, which becomes the base. Now our index number is 2 that we don't write, and the exponent to which this is raised is 1 that we don't write either. So our exponent becomes our numerator. Our index number is our denominator. And there it is in exponential notation. All right, for number 7. Notice that this is a square root of something, and they're asking to determine the domain of this function. Well, we're looking for a real number, so remember we can't have a negative number under the radical sign. That the square root of a negative number is not a real number. So what we do is we equate our radicand to 0. I'm transposing that to this side. I get a positive 6x. I'm going to divide both sides by 6, so I get x equals 2. So I'm putting this on a number line over here. Now, when we solve this for 0, we get a 2. So we know that 2 is in our number set, but can it be greater than 2 or less than 2 to make this statement always positive? Well, if this is 2, a negative 6 times 2 is a negative 12. 12 minus 12 is 0. So we know 2 is in the domain. Now if we make this a 3, negative 6 times 3 is a negative 18. So that would make this a negative 6 under the radical sign. So we know that 3 is not in the set. How about if we make it a 1? Well, negative 6 times 1 is negative 6, and 12 makes this a 6. So that would be, how about if it were a 0? Square root of 12, that's good. How about if this were a negative 1? Now, negative 6 times negative 1 makes this a positive. So that's good. So the domain then of this would be all numbers, as we had used before, including a 2, and that would be the graph of it. Now, interval notation for this would be from negative infinity up to 2. And set builder notation would be x is such that x is less than or equal to 2. Now hopefully you understood, and of course we would have covered some of these in class. Now here they want you simply to expand this so that it's x squared. Well, that special method then of squaring this was this becomes a 16. We're going to multiply this together, get a negative 4, the square root of 2, double it, a negative 8, the square root of 2. And then a negative square root of 2 times a negative square root of 2 gives you a positive square root of 4, which is a plus 2. So these are like terms at the end. So for number 8, this becomes 18 minus 8, the square root of 2. Now for these next few, we want to go over some of the basic operations we have when we are simplifying radical expressions. So, strategy. What we want to do here is to divide or separate into factors those factors of 32 that are perfect third powers. So we have an 8 there and a 4 there. Now 8 is a perfect cube. Now a perfect cube out of a to the 5th would be a to the 3rd, and the part that's left over would be a to the 2nd. And b to the 6th would be a perfect cube, and there would be a b left over. So you've divided the radicand up into factors. Those under the first radical sign are perfect cubes, and then what's ever left. So now you take the cube root of 8, which is 2, cube root of a to the 3rd, which is a, cube root of b to the 6th, which is b to the 2nd, and you just write this one. All right, here, both of these are perfect squares now. Square root of 9 is 3. Square root of this is x. Square root of 16 is 4. A to the 4th, remember there's a 2 here. He's going to divide 4 divided by 2 gives you y to the 2nd. Now here they want you to multiply and see what you get out of this. Well, there's no perfect cube there. So this is going to be the cube root of 18 x y squared. So we just multiply the radicands, so long as our index numbers are the same. Now for this one, the technique is to put this all under a common radical sign. Simplify. Here the x squares will cancel with that, and we're just left with an x there. And here where you subtract that, we get y to the 3rd. And I guess that's about as far as you can go. So as we look at number 13, here the index number is 4. Here the index number is 2. So we can't multiply the radicands as we would do if the index numbers were the same. But if we convert it from radical notation to exponential notation, we can then work with the exponents very well. Keep in mind, in order to do anything with them, though, we have to make these common denominators here. So it looks like our common denominator is going to be 4. So this becomes 2/4, and this becomes 2/4. Now we can work with our fractions here. This becomes x to the 5/4, and this becomes y to the 4/4. And now we convert that back into, well, let me show you an intermediate step here. So this would be x to the 4/4, y to the 4/4, and notice there's 1/4 left over here, so I'll put that over here, y to the 1/4. Okay, now what is 4/4? That is a 1. So that just comes out as an x to the first. This is going to be y to the first. And then we have this to put back in radical form. It'll be the 4th root of x. Now in number 14, again, the index numbers are not the same, but fractional exponents can help us work with this. This is going to become a to the 3/4, a to the 1/5. We bring this exponent up to our numerator, it changes its sign, and we can just subtract, but we can't subtract until we have a common denominator of 20. So this is going to be 3/4 to make our 4 a 20. I got to multiply by 5. So this is going to be 15/20, and this is going to be 4/20. So this gives me 11/20 when I subtract 15 and then a minus 4 gives me an 11. Now back in radical notation, our new index number will be 20. A is our base, and our exponent is to the 11th power. That's for number 15. All right, continuing here, since our radical is exactly the same, the rule is we just deal with the, in a sense, the numerical coefficients. So 11 minus 4 is going to be 7 and the square root of 3. Now for number 16, our index numbers are the same, but our radicands are not the same. But notice here we can take out an x squared. So we get x, the square root of xy, out of this one. I'm not doing the step that you probably should do if you were just starting, but we're moving ahead here. So 5, square root of 25 is 5. Now, under the radical sign, we're going to have an x there. We're going to take out y to the 4th, which becomes y squared, and we're left with a y underneath. Now, in a sense, since these coefficients are not the same, theoretically you could leave it this way, or another way, and I think this is what they're looking for, since we have a common factor, we can factor out an x there plus 5y squared, put that in parentheses, and then have our radical, the square root of xy. So in a sense, both of these are correct. We've simplified this, and this is how they're showing the answer to this one. Well, let me raise it up a little bit here. For number 17, they're asking us to FOIL. So let's do the old-fashioned FOIL here. 6 times 3 is 18. Now my outers will be a negative 24 square root of x. My inners, a negative 3 the square root of x. And then my last will be a negative times a negative, so that'll make it a positive 4. Now this is going to be x squared. The square root of x squared just gives you an x. So we have like terms in the middle, so this will become 18 minus 27, the square root of x, plus 4x. And that is correct. Okay. Now here we're asked to rationalize the denominator. Here our denominator, because of the square root of 3, is irrational. And the technique we use for this is we multiply the denominator by its conjugate. Now you may recall a conjugate is exactly the same terms, but the opposite sign, separating the terms. Here it's a negative, there it's a positive. And I might ask, what is this divided by this? Well, the answer is 1. We're allowed to multiply anything by 1 and not change its value. This is 1, but I've chose a special form of 1 so as to rationalize this. So watch what happens as we FOIL. This times this is 49. And then a negative 2 times a positive 2 will be a negative 4. Negative 2 times positive 2 is a negative 4. Square root of 3 times the square root of 3 is the square root of 9, which is 3. So this becomes then a negative 12. We'll leave it like that for a moment. Now we FOIL our top here. And we'll do that down here. 4 times 7 is 28. Now our outers will be plus 8, the square root of 3. Our inners is plus 7, the square root of 3. And our last will be 2, and then this becomes the square root of 9, which is 3. 2 times 3 is 6. So 6 and 28 is 34. And this is going to be plus 15, the square root of 3. And when we do our subtraction here, this is going to become a 37. So let me erase this other part so you don't get all confused there. All right, there's the answer, all over 37. All right, so we have gone from an irrational denominator to a rational denominator. We have rationalized the denominator. Okay, we're now going to do an equation involving radicals. Strategy, get all of your terms on one side. I'm going to transpose that 3 and isolate the radical. Now, in isolating the radical, the strategy to solve this is to square both sides. Here, that special technique of x squared, multiply these and double it, square that is helpful. And since this is a 2 here, and this is a 2, whenever we raise a radical to the power of the index number, then it just becomes our radicand. Now we have a quadratic equation. We need to get all of our terms over to one side. This becomes a negative 10x, and this becomes a positive 21. Now we factor this. X, 3, and 7. They're both going to be negative. And then here we have x equals 7 or x equals 3. And that is correct. Okay. Let's do number 20, and I'll set it up to save a little time. So the same rules apply. We want to isolate, and we could have done it this way, but I like it this way. We're going to take this negative 1, bring it over. It becomes a positive 1 on this side, and then we're going to square both sides. So this squared is x. Multiplying this and doubling it, we get a plus 2 the square root of x, and this becomes a plus 1, and then this just becomes the radicand. Now notice these cancel out, and again we want to isolate the x, so we're going to get 2 the square root of x equals 2. So I transpose that, becomes a negative 1. Now I'm going to divide both sides by 2. I get the square root of x equals 1. I'm going to square both sides. I get x equals 1. And that is correct. All right, so this wasn't too difficult a one. Sometimes they get more challenging than this. Again, if you want to pause the tape and go through all the calculations, we're already up to 29 minutes here. Okay, in these next few here, we read the problem carefully. There's going to be a park whose dimensions are 200 feet this way, 350 feet this way, and the jogger does the diagonal. And in a sense, this is a right triangle, and this is the hypotenuse. So we're going to use the Pythagorean theorem, where we're going to square this side, square the other side. That gives us a total of this many feet, and then take the square root of it and get this. And they want us to get an answer on our calculator where we approximate it to 3 decimal places. So I just didn't do all the work, but showed you how to set it up. And then here we have an isosceles triangle, right triangle. There's your right angle. There, isosceles means these two sides are the same. So this will be 12 squared plus 12 squared is going to equal c squared. And let's check this out here. This will be 144, 144. So that's 288, or in a sense, it's 2 times 144. This is the perfect square, so 12, the square root of 2, is our exact answer. And this would be an approximation to 3 decimal places. Now we're going to get on to number 23. For number 23, you would need the distance formula, which I've written out here for you. I'm sure this is in your notes somewhere. And you just substitute. This is the sub 1s, let's say. These are the sub 2s. And you substitute, and you get a 4 here that you're going to square. You get a 10 here that you're going to square. You add these together. Get the square root of 116 is the perfect answer, or the exact answer. And then this is the approximation to 3 decimal points. All right, for number 24, they want us to find the midpoints, which is just the midpoint formula. Let me put that up here for you. So the midpoint formula, you add your 2 x's, divide by 2, your 2 y's, divide by 2. This is what we've done. So this is 4 over 2 is 2. 14 over 2 is 7. There's our midpoint. Now, as we jump into number 25, we're going into complex numbers, imaginary numbers, where we are allowed to have a negative under the radical sign if it's squared. And we simply convert that, you may recall, to a negative 1 times the square root of 45. So we said this is the letter I, and this is 9, let's see, 9 times 5. So we take out the square root of 9, which is 3, so this will become 3i, is the way we usually write it, the square root of 5. Now, when we are dealing with combining like terms with imaginary or complex numbers, it's just as if it were a variable. So this will be a 3 minus 7i. Now we're subtracting here, so we just change the signs. This becomes a negative 1 and a negative 8i. Now we just combine like terms. So this is going to be a 2 minus 15i. Now this is a little tricky because you can't, when they're complex numbers, just do this. So what we do here is we take out the I out of this one, and we get 4. Square root of 16 is 4. Take out the I from this one, and this is square root of 9, which is 3. Then we go I times I is I squared. 4 times 3 is 12. So we get 12 times I squared. And I'm sure we've said this, that I squared is equal to a negative 1 by definition. So this is a negative 1 times 12 makes this a negative 12. So be careful of that. You have to do it this way when you're dealing with complex numbers. Now, again, standard form of complex numbers is in A plus BI. So we square this, we get 16. Multiply these two together, double it, we get a negative 8i. And then we get a negative I squared. But I squared, we said, was a negative 1. So the opposite of a negative 1 is a positive 1. So this becomes a positive 1 plus 16 is 17 minus 8i. All right, let's raise it up a little bit, because now we're going to do what we call dividing to simplify, and we want to put it in standard form. Now the rule is, when we're sort of like getting rid of the I in the denominator, we're using sort of like rationalizing, but it's not quite that. But we are going to use the conjugate. So complex conjugates are the same as regular conjugates. This will be a 4. This will be a 5i. This will be a 4. This is a 5i. Now, if this were negative, to make it its conjugate, we just make this a plus, opposite sign. So we're going to multiply this by its conjugate. Now, an interesting thing happens. When we do that, no middle terms, so we end up with 16, and this is going to be a negative 25 I squared. But what did we say I squared was? A negative 1. So this is going to become a positive 25. So in a sense, we have converted our denominator from an imaginary number to a real number. And we just FOIL our top. This times this is 20. Now our outers are a positive 25i. Our inners a positive 12i. And our last is a positive 15i squared. But we know that I squared is a negative 1. So this is going to end up being a negative 15 here. A negative 15 and a 20 gives me a 5. And then this is a positive 5i. And our bottom becomes a 41 as we add those together. Now you might say, oh, I'm all finished. And I better watch my signs here carefully. This is middle term here is a 37. I don't know where I got my 5i from there. 25 plus 12 is 37i. That's better. Okay, now you might say, well, that's my answer. Well, it is, but it's not in the correct form because they wanted it in this form. So what we have to do is put 5 over 41 plus 37i over 41. Now it's in the a plus, this is your real number, this is your imaginary number, this is standard form for the complex number. Okay, for number 30. For number 30, they're asking us powers of I. Well, you recall in our class, we said that I to the fourth was equal to a positive 1. So how many I to the fourths do we have here? Well, let's just write it out. I to the fourth, that's 8. I to the fourth, that's 12. I to the fourth, that's 16. I to the fourth is 20. I to the fourth is 24. I to the fourth is 28. So this is I to the 28th times I, which would give me I to the 29th. Well, this is 1 times 1 times 1 times 1 times 1 times 1 times 1, which is 1 times I. So for number 30, the answer is I. And that's the strategy. Okay, looking at these others, I'm assuming that these are given as enrichment. You wouldn't have time during a normal test to do it because we've already done 40 minutes on this one. And I know how to do them already. And I've cut out time. But for something like this, you would have to do what we did up here. And here, you're going to square this. Oh, there's a lot of work there. So we'll pass up those, and that will be our review of the test for Chapter 7.